If you have ever sat in a power systems class, stared at a transformer vector group diagram, and thought, "I understand what it looks like, but I have no idea why," you are not alone. Most textbooks show you the diagrams, but never explain the real reason behind the phase shift. In this video, we fix that.
This video is divided into 3 parts. Part 1 covers the notation. We go through 6 common vector groups and explain exactly what each letter and number means. Part 2 shows the actual winding connections and the phasor diagrams. You will see how the connections create the phase shifts we talked about. Part 3 brings it all together with a real transformer nameplate. We look at a real unit and identify everything we have learned. Let's get started. Part 1. The first one is Dy11. The capital D tells you the high voltage side is connected in delta. The lowercase y tells you the low voltage side is connected in star. And the number 11 is the clock position of the low voltage phasor. So this means the low voltage line voltage leads the high voltage line voltage by 30 degrees. So delta on the high voltage side, star on the low voltage side, and a 30-degree lead on the low voltage. Now, the second vector group, again, capital D, delta is on the high voltage side. Lowercase y, star is on the low voltage side. The lowercase n means the neutral point of the low voltage star is brought out as an accessible terminal. And the number 11 means the same thing as before. The low voltage leads the high voltage by 30 degrees. The only difference between Dy11 and Din11 is that extra lowercase n, that's the neutral terminal, is accessible from outside the transformer. The third vector group is Y0. Capital Y means the high voltage side is connected in star. Lowercase y means the low voltage side is also connected in star. The number 0 is the clock position. Both phasors sit at 12 o'clock, meaning there is 0 phase shift between the high voltage and low voltage sides. Star on the high voltage side, star on the low voltage side. 0 degrees between them. Here, the number 6 is the clock position. The low voltage phasor sits at 6 o'clock, which means it is 180 degrees out of phase with the high voltage. Both sides are star, but the low voltage is pointing in the completely opposite direction to the high voltage. The fifth vector group is DD0. Capital D represents a delta connection on the high voltage side. Lowercase d, delta on the low voltage side as well. The number 0 means the clock position is 12 o'clock. 0 phase shift between the high voltage and low voltage. Delta on both sides, and no phase difference between them. Now, before we move to talk about their phasor diagrams, we have here Dy1. So, capital D, delta on the high voltage side, lowercase y, star on the low voltage side. The number 1 is the clock position. The low voltage phasor sits at 1 o'clock, meaning the low voltage lags the high voltage by 30 degrees. Delta on the high voltage side, star on the low voltage side, and a 30-degree lag on the low voltage. This is the opposite of Dy11. Welcome to part 2. In this section, we look at the actual winding connections and the phasor diagrams for each vector group. We start with Dy11. On the left is the high voltage side connected in delta. The 3 corners of the triangle are the line terminals A, B, and C. The 3 sides represent the windings AA', BB', and CC'. The connection rule is a prime, which is the finish of the first winding, goes to B, the start of the next dot. Then B' goes to C, and C' goes to A. This forms a closed loop with no neutral on the high voltage side. The keynote says the line voltage VAB equals VAA' minus VBB'. The high voltage line voltage is the vector difference of 2 winding voltages. On the right is the low voltage side connected in star. The line terminals are A, B, and C. The finished terminals A', B', and C' are joined at the center, becoming neutral in. The line 2-line voltage VAB is measured directly between terminals A and B. It is taken straight from the winding with no subtraction. On the phasor diagram, the high voltage line voltage points straight up at 12 o'clock. The low voltage line voltage sits at 11 o'clock, 30 degrees ahead. That is the Dy11 shift. The low voltage leads the high voltage. Also, the phasor diagram is exactly the same as Dy11. The low voltage leads the high voltage by 30 degrees. The neutral terminal is an extra connection, not a phasor. DIN 11 is identical to Dy11 in terms of winding connections. The high voltage is delta, the low voltage is star, and the same 30-degree lead is present. The only difference is that the neutral point of the low voltage star is brought out as an accessible terminal. This neutral does not change the phase relationship. It simply allows for wire operation and earthing. For Y0, both sides are star. On the high voltage side, the finished terminals join at neutral. On the low voltage side, it is the same. Because both sides use the same method to obtain line voltages, no phase shift is introduced. The line voltages are directly in phase. On the phasor diagram, the high voltage line voltage points straight up at 12 o'clock. The low voltage line voltage also points straight up. They are exactly in phase. The clock number is 0, indicating no phase shift between the two sides. Y6 also has star on both sides, but on the low voltage side, the polarity is reversed. Instead of joining the finished terminals at neutral, the dot-marked terminals go to neutral. This reversal flips the low voltage by 180 degrees. The high voltage phasor points to 12 o'clock. The low voltage phasor points to 6 o'clock. Exactly opposite. That is the 180-degree shift. Now let's move to DDO. Here, both sides are delta. The high voltage delta uses the same closed loop as Dy11, A prime to B, B prime to C, C prime to A. The low voltage delta is identical. A prime to B, B prime to C, C prime to A. Because both sides use the same delta arrangement and the same connection sequence, the line voltages on the high and low sides end up in phase with each other. There is no net phase shift. On the phasor diagram, both the high voltage line voltage and the low voltage line voltage point straight up at 12 o'clock. 0 degrees between them. The clock number is 0. Dy1 is the mirror of Dy11. The high voltage side is the same delta. The low voltage side is star, but with reversed polarity. On the right is the low voltage star, and this is where Dy1 differs from Dy11. In Dy1, the polarity has been reversed on the low voltage side. The dot-marked terminals A, B, and C are connected to the neutral, and the finished terminals A prime, B prime, and C prime are now the line terminals. This reversal is what changes the group from 11 to 1. The high voltage phasor is at 12 o'clock. The low voltage phasor now sits at 1 o'clock, 30 degrees behind. Hence, the low voltage lags the high voltage. So Dy1 is the mirror of Dy11. The LV polarity reversed on star side. In Dy11, the low voltage was at 11 o'clock on the left, leading, so in Dy1, it is at 1 o'clock on the right, lagging. The only thing that changed between these two vector groups was the polarity of the low voltage star winding. In part 1, we learned what the letters and numbers mean. In part 2, we saw how the windings are connected and how the phase shifts happen. Now in part 3, we bring it all together with a real transformer nameplate. Now, you will see exactly where the vector group appears, what the other ratings tell you, and how everything we have covered applies to a real transformer in the field. If you haven't already, please hit that subscribe button and hit the like button. Let's get into it. Now we are looking at a real transformer nameplate. This is a 400 kVA 3-phase distribution transformer made by Elec. Everything we have studied in this video appears right here on this plate. Starting at the top, the rating is 400 kVA. That stands for kilovolts amperes, the maximum apparent power the transformer can deliver continuously. Think of it as the size of the transformer. The voltage ratio shows 11,000 volts on the high voltage side and 433 volts on the low voltage side. That means when you apply 11,000 volts to the primary, you get 433 volts out on the secondary. This is the step-down ratio. Next. BIL means basic insulation level. It tells you how well the transformer can withstand voltage surges, like lightning strikes. On the high voltage side, it is 75 kilovolts peak. On the low voltage side, it says NA, which means not applicable or not specified for this design. The current ratings are 20.99 amps on the high voltage side and 533.35 amps on the low voltage side. These are the full load currents. Notice the low voltage current is much higher because the voltage is lower. That is why the low voltage windings use thicker conductors. Frequency is 50 Hz, standard for many countries. Now the vector group. DIN11. This is what the whole video has been about. Delta on the high voltage side, star with accessible neutral on the low voltage side, and the low voltage leads the high voltage by 30 degrees. The impedance voltage field is blank on this nameplate. If it were filled, it would be a percentage that tells you how much voltage drops under load and helps with parallel operation. Energy efficiency? Level 2 means this transformer meets a standard efficiency classification. Level 2 is typical for modern distribution transformers. Cooling method, ONAN stands for oil, natural air, natural. The transformer uses natural circulation of oil to transfer heat to the tank, and natural airflow around the tank to cool it down. No pumps or fans are needed. The temperature rise is 40 degrees Celsius for the oil and 45 degrees Celsius for the windings above the ambient air temperature. This tells you how hot the transformer can safely get. The mass and volume values are useful. For installation and maintenance, the transformer contains 447 kilograms of oil, has a total mass of 2,148 kilograms, and holds 550 liters of oil. The tap changer table at the bottom shows 7 positions. This is an off-circuit tap changer, meaning the transformer must be de-energized before you change taps. The taps let you adjust the high voltage input from 11,825 volts down to 10,175 volts in steps of 2.5%, while the low voltage output stays fixed at 433 volts. This allows you to compensate for variations in the supply network voltage. Finally, at the bottom right of the nameplate, you can see the vector group diagram drawn directly on the plate. The delta triangle is labeled 1U, 1 volt, 1 W for the high voltage side, and the star shape is labeled to U, 2 volts, 2 W for the low voltage side. This is the visual confirmation of the DIN11 vector group printed right on the transformer itself. That is it for transformer vector groups. We covered the notation, the connections and phasors, and then saw it all on a real nameplate. Now when you see a vector group, you will know exactly what it means. If this helped, hit subscribe and tap the bell. More electrical content coming. Thanks for watching.